a credit assignment compiler for joint prediction. Many applications require a predictor to make coherent decisions. For example, consider recognizing a handwritten word where each character is recognized in turn to understand the word. Exposing information from related predictions, such as adjacent letters, aids individual predictions. Also, optimizing a joint loss function can improve the gracefulness of error recovery. Methods making a sequence of sub-decisions have been proposed for handling complex joint predictions. These methods decompose the production of the joint output in terms of an explicit search space. In the test time, beginning at the start state, an agent chooses the next state based on the learned policy. The process stops when the agent reaches an end state, at which point the loss is collected. The training is essentially done by trying out different versions of policies to learn one that yields low loss. Learning to search approaches figure out the credit assignment problem. That is, when something goes wrong, should we blame the first, second, or third prediction? They have shown promise both in theory and in practice. However, specification of a search space as a finite state machine is awkward, and naive implementations do not fully demonstrate the ability of these methods. In this paper, we show the search space can be defined by an arbitrary imperative program. Turning learning to search into a credit assignment compiler, which translate the user-specified decoding function and labeled data into updates of the learning model. Together with several algorithmic improvements, this radically reduces both the complexity of programming and the running time. The programming interface allows to use the same decoding function for training and prediction, preventing common train-test asynchrony bugs. The compiler automatically ensures the model learns to avoid compounding errors and makes a sequence of coherent decisions. Moreover, the library functions are in a reduction stack, so as base classifiers improve, so does joint prediction performance. This is sample code for a generic sequence labeler. The algorithm takes as input a sequence of examples, and predicts the label of each element in turn. It uses two underlying library functions, predict and loss. Predict returns individual predictions based on input, while loss allows the declaration of an arbitrary loss for set of predictions. The reference policy, which used only in the training phase, point a suggestion as to a good next state for each state. A decoding algorithm for a complex decision problem can be implemented in a similar way. We implemented the credit assignment compiler at Vopa Wabbit, a machine learning system. See our paper for details.